Hello, everybody, and welcome to this webinar brought to you by Learning Space Tuition. My name is Heinrich Cox. I am the academic manager here at Learning Space, and I'm excited today to be doing this webinar with you. We're going to be looking at forces and Newton's law. Right, so first things first, this webinar is absolutely free. And you've got the link in order to join this webinar, otherwise you wouldn't be here. So please, if you have friends or anybody from school who you think would benefit from being here, please feel free to share that link with your friends. They will be able to use that link in order to join us here today and hopefully get some benefit out of this as well. Right, so very quickly, I just want to tell you about Learning Space Tuition. So we are a tutoring company and we specialize in maths and physical science tuition for grades 1 to 12. So we either do private lessons where it's just you and your tutor for 1 hour, either online or at our branch in Bryanston, or we do small group lessons where there are a maximum of 3 students with 1 tutor. Right, so the other thing I want to share with you is that this webinar is actually part of a series. So we are going to be doing a functions webinar on the 16th of September and a stoichiometry, quantitative aspects of chemistry, in other words, webinar on the 29th of September, right? So signups for those webinars will be open up until the time that we deliver those webinars. So again, if you find value in this one here today, please join us for those other ones, but also tell your friends it's free. It's a nice way to spend a Wednesday afternoon. Right, then some housekeeping. We've got some ways in which you can interact with us. So one is the chat feature. So the chat feature you can use in order to post messages that you would like the whole group to see. The Q&A feature you can use in order to ask me questions. Now, the questions that you type there, I'm not going to answer as you type them. We've actually got a tutor on standby who will be monitoring those questions and then hopefully be able to type a response to you if you do use that Q&A function. If, however, it is a question that it's best for me to answer, then we'll leave it until the Q&A session at 6:30. So an hour and a half into the webinar, where I will then be able to answer that question and be able to take questions live from you, the audience. Right, then we also have a polling feature in which we will be able to put up a poll where you will then be able to select some answers and feed that back to us in order to keep things nice and interactive. Okay. So I think the most appropriate thing for us to do at this stage is to then actually get started, right? So there you go, forces and Newton's laws. I didn't lie, the PowerPoint says so. The first thing I would like for us to do is to look at the introductory poll. So please, let's look at the introductory poll and get some information there that'll be useful to us going forward in this webinar. Fantastic. We've got answers coming in on this side. We'll give you another 30 seconds just to finish up and make sure that you're happy with your answers. Okay, so I think we can end the poll there and have a look at the results. So if we have a look at the results there, it seems that most of you are joining us from Gauteng and many of you from Limpopo as well. I'm very happy to see that there's that one person who's from the Eastern Cape. I am myself a Gqeberha boy, born and raised, and doing my time up here in the north in Joburg, but always happy to go home. So very nice to see that we've got somebody joining us from the Eastern Cape and mostly from all over the country, right? So we've got 7 of the 9 provinces represented, and I'm sure people will still join as we go along. So I see that there are a lot of these topics that you guys find challenging, and hopefully we're going to find that those things change as we continue with this webinar. So let's get going and actually look at the material. Right, so where shall we start if not at vectors and scalars? Right, so a scalar is something that has magnitude only, so size or scale. You can describe it with a number, how big it is. Whereas vectors are those things that have both magnitude and direction. So because it has magnitude and direction, it's actually really easy to represent it with an arrow. So the arrow points in a direction, right? So that gives you the direction. And then the length of the arrow represents the magnitude. So a longer arrow means a greater magnitude, and a shorter arrow will mean a smaller magnitude. Now, just so you're aware, if you multiply a vector by a scalar, the result is also going to be a vector. So one that you might know of if you're in matric is momentum, where you take mass and you multiply it by velocity and you get the vector momentum. Then we can look at just a list of vectors and scalars. So vectors are things like displacement, velocity, acceleration, force, momentum, impulse, and even electric field. Whereas scalars are things like distance, speed, mass, work or energy, and time. So what's super interesting here is that we're going to focus mainly on force, since this is a forces and Newton's laws webinar. So if we have vectors, what's your vector, Victor? If you have vectors, you'd like to possibly add them together. Right, so vectors are most easily added together when they are acting in the same line of action, right? So if they're acting in the same line, right? And the golden rule for adding vectors is that vectors should be added tip to tail, right? So the resultant vector, the net vector, that is the one that starts at the start and ends at the end if we go do this tip to tail thing. So let's see what that looks like. So let's say we've got these 2 vectors that's acting on that point there, that pink dot, right? And we want to add these together. What we would do is draw them tip to tail. So the tail of the one vector goes to the tip of the other one, as we have there. And then the resultant vector starts at the start of the first one and ends at the end of the second one. And so that pink vector there is going to be the resultant vector. So let's make it numerical. Let's say that first vector was 10 newtons to the left and the second was 4 newtons to the right. If we are going to add together vectors, we've got to take into account that they do have direction. And so we need to nominate a positive and a negative direction if we're going to go and add vectors together. So I'm just going to take here leftward as being positive and rightwards as being negative. So then if I want to go calculate Fnet, I can go positive 10 minus the 4 and get an answer of positive 6, which then means that my resultant vector in this instance is going to be 6 newtons to the right. Okay, so it's easy if they're in the same line of action, but what if they're not? So let's say, for example, we've got these 2 vectors that's adding on that point there. How on earth can we find the resultant vector? Well, fortunately, the rules don't change. So if we want to add these vectors together, we can draw them tip to tail, and then the resultant vector starts at the start of the first one and points towards the tip of the second one, right? And it doesn't even matter what order you add the vectors in. So here we added the long one first and then the short one. But if we add the short one first and we then add the long one to it and draw tip to tail in that method, we still get exactly the same resultant vector. So it doesn't matter which one you draw first, which tip you put to which tail, as long as you draw your vectors tip to tail when you are adding them together in order to find resultant vectors. Now, we need to clearly differentiate between the two diagrams that we're seeing on the screen, right? Now, when you have the tails of your vectors on the same point, that means you are showing those forces or those vectors acting on that point. So that's what it looks like, for example, if two forces are acting on an object. When we go and draw them tip to tail, that's when we're adding them together, right, in order to then find a resultant force, okay? So if we want to show forces acting on an object, we put the tails on the object, here represented by a dot and often represented by a dot in free body diagrams. But if we want to add forces together, we have to draw them tip to tail. Okay, so let's talk about components of forces. So in the same way that two vectors can be added together to give one vector, a resultant vector, one vector can be broken up into two vectors that would add together to give the original vector, right? So these forces, these two things that you add together to get the original, those are called components. And components is just a word that means parts of. And surely when you put the parts of something together, you get again the whole. So it's taking a vector and breaking it into two parts, which are often more useful than the original vector just by itself. So let's say, for example, we've got this wooden block here, and we've got this guy who's pushing it, and as a result, the block moves in that way. If we go and have the same block, but instead we have one person pushing horizontally in the rightwards direction, and the other person pushing vertically in the upwards direction, it is possible for that block to move in exactly the same way, right? So these vectors have to, in fact, be equivalent then because they moved the block in the same way. So that diagonal vector there, that would be our resultant vector, whereas the vector going to the right and the vector going up, where those two together give us that resultant vector, those are what we would call the components of the vector. So those two vectors, the horizontal and the vertical one together, is exactly the same in terms of how it's going to affect the object as just having that original diagonal vector, right? So in terms of terminology, we often just call that original slanted vector F, and then the horizontal one we call the X component, and the vertical one we call the Y component. And the X component and the Y component there, those are our components of that vector F. So again, Fx and Fy acting together is exactly the same as F acting by itself. Okay, so time for an example. Let's see how we can go and find the components of this vector here. Right, now the first thing we need to do is realize that we want to draw our X and our Y components as being added together. So we've got to draw them tip to tail. And if we draw them tip to tail, we'll get a triangle that looks something like this, and it's got to be a right angled triangle. Right, so then in a right angled triangle, we know that the side opposite the 30 degrees there is going to be that one, which we call Fy, right? And then adjacent to it, next to it, we're going to have Fx. Okay, so here we then get to use trigonometry. So if we, for example, go cos 30 is the adjacent over the hypotenuse, right? Which is going to be the Fx over this original force, the 15 newtons. And in other words, to find Fx, we then just have to go 15 multiplied by cos 30. And for the sake of completeness, let's grab our calculators, go 15 times cos 30, and we'll get an answer of 12.99, which will, yeah, actually, we've got to leave it as 12.99. How frustrating is that? Okay, so 12.99 for our X component. And then to find the Y component, because it's opposite that 90 degree, opposite the 30 degree angle, that's when we use sine. So sine of 30, right, we're going to go and say it's Fy, the opposite, over the hypotenuse, which is 15, right? And then we get 15 times sine 30 is equal to Fy. And you might know your special angles and know that sine 30 is a half. So that then means that 7.5 newtons is equal to Fy. Okay, so that's how we would find the components of that vector there. So basically, whenever we're trying to find an adjacent component, the one next to the angle, we use cos. Whenever we try to find the opposite component, the one that's opposite the angle, we use sine, right? And we often take the shortcut of just taking the force itself multiplied by sine of the angle. If we're looking for the one opposite the angle, for example, it's basically just skipping this step of writing first the trig function as the subject of the formula. Okay, cool. So let's continue here. Now we're going to try and find the components of gravity, right? So for gravity, gravity always acts vertically downwards into the center of the Earth. If you draw a gravitational force and it's not going vertically downwards into the center of the Earth, then you've got a problem. Okay, now Fg, we know, is equal to the mass of an object multiplied by gravitational acceleration. So Fg in this instance here would be 5 times 9.8, and 5 times 9.8 should be 49 newtons. Okay. So there we go. That's our Fg. So that's our original vector, the one that we want to find components of. Now, when we try to draw our x, well, here we're not going to break it into an x component and a y component. We're actually going to break it into a perpendicular component and a parallel component. And the reason for that is that it's way more convenient to have forces that are parallel to the surface or perpendicular to the surface, as you'll see as we go along, right? So for our components, we basically always want to break it into components that are parallel to the surface and perpendicular to the surface. It just so happens that often it's a flat surface, and then those components will be x components and y components. Okay, so a common mistake here is that people like to go and draw this vector diagram like this, right? And the issue with this vector diagram that I've drawn here is that 49 is not the hypotenuse. If you go look, you'll see that 49 isn't the longest side in that triangle. And so it can't be the hypotenuse, so we wouldn't really be finding the perpendicular and parallel components. So what we need to do is to make sure that when we draw this vector triangle, we do it nicely such that this here and this here actually forms that perpendicular angle, right? The 90-degree angle. And this here is what we'd call FG perp or perpendicular, and that's because it's perpendicular to the slope that it's on. And then this here is going to be FG parallel. Okay, so I don't usually advocate that you just memorize something, but in this instance here, it's a lot easier to just remember that the angle between FG and FG perpendicular is always going to be equal to the angle of the incline, rather than going and proving it for yourself every time. Okay, so the angle between FG and FG perpendicular is going to be the same as the angle of the incline, and that's this 30 degrees here. Okay, so to find this FG perpendicular, right, we now know that FG perpendicular is adjacent. It's next to that 30-degree angle. And because it's next to, we use cos, right? So that's then going to be FG times cos 30. And FG we've already calculated. So it's going to be the 49 times cos 30. And then once again, we'll defer to our calculators who always know best. 49 times cos 30 gives us 42.44. Okay, so 42.44 newtons. Okay, and then FG parallel, because we're now dealing with the one that's opposite the 30-degree angle, we've got to use sine. So that's going to be equal to FG times sine of that angle, sine 30, right? And that's going to be 49 times sine 30 again is a half, right? And that should give us 24.5 newtons if my mental math is correct. Okay, so what does this mean? It means that if you have a 42.44 Newton force going in that direction, and you've got a 24.5 Newton force going in that direction, if you add those together, it's got exactly the same effect as this FG here, right? So these are now our components of FG. Awesome. Okay, so now it's time to do a slightly more complex example. Now, when we've got vectors like these that we're trying to add together, the issue that we have is it's kind of difficult if we just draw them tip to tail to go and find the length of the other vector without using the sine rule or the cos rule or anything like that, which we really don't want to do. So because we saw at the start, it's easiest to add together vectors that are in the same line of action. What we do is we take our vectors and we break them up into x components and y components, because those x and y components are then easy to add together, right? So we're going to find the x and y components of each of these forces. We're going to add together the x components to find a resultant x component and add together the y components to find a resultant y components. And we're going to use those two resultants in order to find the net force. Okay, so now I've gone on too far, so let me go back. Okay, here we go. Let's do this. Okay, so this 30 Newton force, we want to break into an x component and to a y component. So here's fx, here's fy. Okay, so fx is next to that 25-degree angle. So we know we've got to use cos. So this is going to be 30 times cos 25, right? And then our calculators will tell us that 30 times cos of 25 is 27.19 newtons. So 27.19. Okay, and then fy, we've got to use sine because it is opposite that 25-degree angle, right? So this is going to be 30 times sine of 25. Let's see what we get. 30 times sine 25 is going to be equal to 12.68 newtons. Great. So now we've got the x and the y components for our 30 Newton force, and we want to do the same thing with the 15 Newton force. So for the 15 Newton force, I'm going to draw my diagram like this. I'm going to put my y component there. I'm going to put my x component there. And then, okay, the diagram makes it a little bit difficult to see, but this here is that 20-degree angle. All right. So here, the y component is in fact next to that 20-degree angle, which means to find the y component, we actually have to use cos. But what I'm going to do is I'm just going to use a different color here so that we don't confuse our fx's and fy's. So this here is fy, and this here is going to be fx, but the y component we find using cos because it's next to that 20-degree angle. So just as an aside here, I find that people often try to memorize that vertical is sine, horizontal is cos, or something like that. Now, the reason that I'm showing you that it actually depends on the triangle is so that you can understand why you are doing what you're doing and then be able to work with those less common ones where the vertical is actually going to be found using cos and the horizontal is using sine. And that's actually what's happening here with this 20-degree angle. All right, so the y component is next to the 20 degrees, right? So to find this fy, we have to go 15 times this cos of 20 because it's next to, it's adjacent. Okay, and let's see, 15 times cos of 20 gives us an answer of 14,10. Right, and then fx is now going to be using sine because the x component is opposite the 20-degree angle. So this is then sine of 20. So let's see, 15 times sine 20 gives us 5.13. Okay, and here it might be useful just to note that this here is to the right, this here is up, this fy here is down, and this fx here is left. Okay, so basically what we now have is instead of these two original vectors, we've got the four components, right? So we've got one fx going this way, we've vector, or what I called here resultant x and resultant y. Okay, so the resultant y if we see here, we've got 14.10 going down and 12.68 going up. So we've got more going down than we do have going up. So if I take down as my positive direction, I can go 14.10 minus the 12.68, and that gives me a resultant y vector of 1.42 newtons down. Okay, so that's then my resultant y vector. And then my resultant x vector, right, is going to be, let's see, we've got 27.19 going right, 5.13 going left. So here we want to take rightwards as being the positive direction. Okay, so then we have the 27.19 going right minus the 5.13 going left, and then our resultant is going to be 22.06 newtons going right. Okay, so now we've got a resultant y vector and we've got a resultant x vector, and we use that in order to then go find the actual resultant, right? So here we can draw another free body, well, not a free body diagram. We want to draw a force diagram where we're actually adding the stuff together. So if you add up 22.06 going this way, and you add up the 1.42 going this way, we've now drawn them tip to tail. So the resultant is what we get when we start at the start and end at the end. And you might notice here that actually we've got a right angled triangle where we have two of the sides. And when you have a right angled triangle with two of the sides, you can use Pythagoras. So we're going to use Pythagoras in order to find the length of the resultant there. So we'll then just take the square root of the 22.06 squared plus the 1,42 squared. And that, using Pythagoras, gives us a resultant of 22,11 newtons. So that's the resultant there. And then if we want its direction, we need to find this angle here, theta. So to use that, to find that theta, we'll need to use trig. So we'd go tan theta is equal to the opposite over the adjacent, which is then 1.42 over the 22,06. And then we can use the inverse tan function. So inverse tan of that 1.42 over 22,06 is going to give us theta. So let's see what that is. So inverse tan of 1.42 over 22.06 gives us an angle of 3.67 degrees. Okay, so this is 3.67 degrees. So our final answer then is that F net is equal to 22.11 newtons, right? And the angle is 3.67 degrees. And then we know that it's pointing somewhere in this direction. So if we call this east, then we are heading to the south of east. So it's 3.67 degrees south of east. Okay, and that's how we take two complicated vectors pointing in what sort of different direction, and we actually go find a resultant vector. Easiest thing to do, break both of them up into x and y components, find the resultant x, find the resultant y, and then add those together in order to find the new resultant vector. Okay, so now it is going to be your turn. You've got that diagram there, 10 newtons to the right, and then 40 newtons down to the bottom there. See if you can go find the direction and the magnitude of the resultant vector. Okay, giving you 5 minutes. All right, there we go. I hope all of you had a chance to at least attempt it and have a good idea of what direction you're going in. Right, so I'm going to end the poll there and I'm going to share the results. So if we have a look there, we've at least got some representation for all the answers. So the popular choice is 42 newtons at 40 degrees south of east. Let's see whether those of you who selected that are in the right. And I hope this doesn't say anything about democracy if the majority don't end up being right. So let's do this. Let's see here. Okay, so here, we're lucky because this 10 Newton force here is already an X component. It's, well, not really a component because it's the original force, but it's in the X direction. So we don't need to do anything with it. So only this 40 Newton force here do we actually need to go break up into an X component and into a Y component so that we can easily add those together. Right, so the X component there is next to the 30-degree angle. So the X component is going to be the 40 newtons times next to adjacent means we've got to use cos. So cos of 30, and let's see, 40 times cos 30 is equal to 34.64 newtons. Okay, so we've got 34.64 newtons there. Okay. And then in order to find the Y component, right, we now have to use sine because the Y component is opposite that 30-degree angle, right? So now we go 40 times sine of 30. And again, 40 times sine 30 is 40 times a half. So that's then 20 newtons, right? So what we now have is actually an X component going this way. That's 34.64, right? We've got the other force still going that way, that's 10 newtons, and then we've got a force going down, that is 20 newtons, right? So these diagrams are pretty much equivalent. Instead of having the 40 Newton force, we've broken up the 40 Newton force into its two components, and now we can add together the X component. Resultant that starts at the start of the first one, ends at the next one, and has that 90-degree angle there. Right, so same thing, you're going to use Pythagoras, right? So r squared is equal to the 24.64 squared. Good luck to those of you trying to read that. Plus 20 squared, right? And then if you go solve for r in that equation, you take the square root of 24.64 squared plus 20 squared, we get an answer of 31.74. Okay, so 31.74 newtons was in fact the resultant force. So democracy failed us in that instance there. And then here we just need to find this angle so that we can get the direction. So we can use tan theta, which is equal to the opposite over the adjacent. So 20 over the 24.64, right? And then if we use the inverse tan function of that 20 over 24.64, then we get an angle of 39.07 degrees. So theta is 39.07 degrees, right? And so this 31.74 newtons is at 39.07 degrees. And again, it's pointing somewhere in this direction. So that is east, then this is south of east. So this is south of east. So well done to those of you who tried it, and well done to those of you who got it correct. Okay, we'll be using these skills as we go on in this webinar. So if you don't quite get this one correct, it's fine. You're going to see the same sort of thing breaking down into components over and over again. And that's really how you learn. You get things wrong, you understand why you got them wrong, and then you try to get them right the next time. Cool. Right. So now, Newton's laws. Okay, so we can talk about Newton's first law. And that is that an object at rest, or that's moving with constant motion, will remain at rest or continue with constant motion unless a net force is acting on it. Okay, so that's wordy. What does it actually mean in English? It means things continue to do what they do unless we do something to them. Okay, if something's just lying there, it's going to continue lying there unless you push it. Something's rolling down the hill or whatever it is, it's not going to stop rolling down the hill unless you, well, stop it, something like that. Okay, so in mathematical terms, it means that F net is equal to 0. In other words, all the forces are going to be balanced because there's no net force acting on it. And this happens, right, when we're moving at constant velocity or we're not moving at all. So our strategy here is going to be to find all the forces in that x direction, or that's parallel to an inclined plane, and all the forces in the y direction, or, you know, what's perpendicular to an inclined plane, and we're going to set them equal to each other. And when do we use this? Well, as I said, whenever the object is not moving. So if the object is stationary, then F net is 0. Or if the object is moving at a constant velocity, then F net is also 0. Constant velocity, sometimes called unchanging velocity, but basically the speed or rate at which it's moving remains the same. Cool. Let's look at an example here, right? So we've got an outrageously heavy light bulb of mass 2 kilograms that is hanging from a ceiling in the following manner. We've got to find the force of tension in each of the wires that are attached to the ceiling. Okay, so we've got these two wires and we've got to go now and find the tension forces. Okay, so here is one tension force going that way. Here's another tension force going that way, right? And then there's this force here going down, and that force is due to the mass of the light bulb. So we already know that that's Fg, right? And we can already just calculate it here. It's going to be 2 times 9.8, right? And it's going to be 19.6 newtons. Okay, so we already know this force going down. So if we use our first law principle, then we know what we want is for all the forces in the x direction to be balanced and all the forces in the y direction to be balanced, right? But in order to be able to do that, we first have to go and find components. Okay, so here, let me color code it here with the two tensions. Okay, so red for the one on the left. So if I draw this Fy here, along with this Fx here, this here would be the x and y components for this tension going off to the left, right? So we see that we have a y component, x component, we've drawn them tip to tail, and you've got the 20-degree angle there. Do not despair if you prefer to draw the triangle like this. Okay, you absolutely can draw the triangle like this, and then use the fact that you've got alternate angles being equal to say that that is 20 degrees, right? You more than welcome to do that. There's always two possible force triangles that you can draw for the resultant. It just depends whether you first draw vertical, then horizontal, or first horizontal, then vertical. Okay, so I did it this way just so that I don't have to think about the 20-degree angle. Okay, so this 20-degree angle is opposite that and next to that, right? So I know that the y component of, and let's call this T1, the y component of T1 is going to be T1 times, and now because it's opposite the 20-degree angle, that's going to be sine of 20, okay? And then the x component is going to be T1 times cos of 20 because that x component is next to the 20-degree angle, right? Then if we go and do the other one, then we can do the same thing, right? So here you'll have a y component going up in that direction, right? And you'll have an x component going towards the right there, right? And now in this case here, if we go and look, this 50-degree angle is opposite that y component. So for this one here that we'll call T2, for T2, Fy is going to be equal to, Fy is going to be equal to T2 times sine of 50. Because again, that component, that y component is opposite the 50-degree angle, right? And then Fx is going to be T2 times cos of 50 because it's adjacent or next to that angle there. Okay, so we've now found those components and the question is why, right? Now, the reason is the following. We said that when an object is at rest or moving at constant velocity, the net force acting on it is 0, zip. That means that all the forces have to be balanced, right? And that means that the forces going up and down and the forces going left and right have to be balanced. Okay, so I'm going to divide this into two lines of action, right? I'm going to divide it into the horizontal and the vertical. Okay, and because the forces are balanced, that means for horizontal, the forces going right is the same as the forces going left, right? So Fx going right must be the same as, well, the Fx for the other one. Let me be consistent and call it the Fx there going left that I've done color coded. In a test or exam, you obviously can't color code, so you'll write Fx T2, Fx T1. I'm trying to keep it simple, sue me. Okay, cool. So then for the vertical ones, right, we've got forces going up. So what do we have going up? We've got Fy from the red, that's going up, right? We've got Fy from the purple, that's going up. And because the object's not moving, it's balanced, Newton's first law, that means the horizontal and vertical components all need to be balanced. So that's got to be equal to the Fg going down. So that's got to be equal to Fg. Okay, so now we've got two equations. What on earth can we do with the equations? Okay, so now I'm no longer going to color code it. I'm just going to go substitute in, right? So that Fx was T2 cos 50. Okay, and the red Fx, which was this one here, that was T1 times cos 20. Okay, and then here, I'm just going to give myself a bit more space. Fy was T1 sine 20. The other Fy was T2 sine 50. And that was equal to the Fg that was 19.6 going down. Okay, so what do we have here? We have two equations, and in both equations, we've got the same two missing variables. We've got T1 and T2 in the one equation. We've got T1 and T2 in the other equation. So those of you who love math as much as I do, or even, just a portion of as much, you might be getting very excited at this point because two equations, two variables, you can solve simultaneously. And that's exactly what we're going to do here. So when we do this, we want to make one of the things the subject of the formula, right? So here, for example, let's make T2 the subject of the formula. So T2 would now be equal to T1 cos 20 over cos 50. And then wherever we see T2 in the other equation, we need to go sub this in, right? So then our T1 sine 20 plus T2, oh, not plus T2, undo, let me erase that. Sorry, where we see T2, we need to put in what we've got there. So where we see T2, we put in T1 cos 20 over cos 50 times the sine 50. And that's equal to the 19.6, okay? And now I'm going to use my calculator to add up those coefficients of T1. So we've got to go sine 20 plus the coefficient of the other T1, which is going to be cos 20, cos 20 over cos 50 multiplied by sine 50. And that means the coefficient of T1 is going to be 1.46. So 1.46 T1 is equal to this 19.6. And then we can just divide both sides by 1.46 in order to get T1. So 19.6 divided by answer gives me 13.41. So T1 is equal to 13.41 newtons. Perfect. And then T2 is quite easy to find. We just have to go sub in again for T1. So 13.41 cos 20 over cos 50. Right. 13.41 times cos of 20 over cos of 50. And so we get an answer of 19.61 newtons. Okay, so it looks like a lot, right? But we took some steps that are easy to understand and easy to use in future, right? So where did we start? We saw this light bulb is not moving. Okay, so we applied Newton's first law and we said the light bulb's not moving, it's at rest, F net is equal to 0, right? Then we took all the forces that are not horizontal, well, vertical and horizontal, and we broke them up into components that are vertical and are horizontal because those are easy to add together. And then because Fnet is 0, the object is at rest, we could say, fine, all the horizontal forces balance out, all the vertical forces balance out, and that allowed us to write equations. And once you can write an equation that's correct, all you've got to do from there is solve. So in this instance here, we had to solve simultaneously, but in other instances, it's not going to be that complicated, and you can solve a single equation. Right, so then it is your turn. I am once again going to ask of you to attempt this question over here. I'm going to give you 4 minutes. Give it a go. Okay, right. So let's see what we've got here. So I'm ending the poll now and I'm sharing the results. And here again, we've got some options or some votes for each of the options, which is nice that all the candidates are being represented, right? And the most popular answer here is the 21.13 newtons down. Okay, now for those of you who selected option 2 and option 4, you are on the right track because the question said find the mass of the lampshade, right? And mass is something that is measured in kilograms. And perhaps those of you who went option 1 and option 3, you might have calculated the weight, which is the force of gravity that's acting on a mass, right? So let's see here how we get the answer, right? So soon as this pen works, right? What we've got here is, again, a Newton's first law scenario where the forces are balanced, right? So here, the forces in the up direction and the forces in the down direction must be balanced, and the components of the forces going that way and the components of the forces going that way must be balanced. Now here, because we're just trying to find the mass of the lampshade, this isn't necessarily particularly interesting to us, so we're just going to find this here, right? So if we look at that force, now I'm redrawing it, even though it's there, you've got the, oh, that's the 50 newtons. You've got 25 degrees here, so, okay. We can draw Fx like this, and we can draw Fy going up like that, and then you'll see that the 25 degrees is opposite the Fy side, or the Fy side is opposite the 25 degrees, which means we use sine. Okay, so that Fy going up, we're going to go the force, which is 50. Oh, okay. Sorry, let me just go back here. Yeah, the force that is 50. Multiplied by the sine of 25, right? And then we go 50 times sine 25, and we get an answer of 21.13. Okay, so 21.13, right? And now in that vertical line of action, we know that this y component going up must be equal to Fg going down, right? So if this is 21.13, then in order for them to be balanced, Fg going down has to be 21.13. But we're trying to find the mass and not the weight. So we know that Fg is equal to mg. 21.13 is equal to the mass, which is what we're trying to find, times 9.8. So then we've got to take this 21.13, divide it by 9.8, and we get an answer that the mass is 2.16 kilograms. Okay, so don't confuse the two things. Mass is a measure of how much matter is in a particular object, right? So 2 kilograms on Earth is 2 kilograms on the moon, is 2 kilograms in Jupiter, wherever. It's always 2 kilograms. Whereas weight is the force of gravitational attraction that's being exerted on a mass. And that's measured in newtons, and that's the one that's different on different planets. Okay, let us continue. So here, one of the big barriers to success that students have in this section is not really understanding this normal force, right? So let's talk about the normal force. The normal force is the force of the surface the object is on acting on the object, right? So it's surface on the object. The normal force is always perpendicular to the surface. And without the normal force, objects would literally fall through the surface, right? So if you're standing on the ground, the reason you're not falling through the ground is the fact that the ground is exerting a force back up against you that is preventing you from falling through the ground to the center of the earth. And then note this, please. The normal force is not always just equal to the force of gravity. And we're going to unpack that misconception in detail. And then the Newton's third law pair of the normal force is the force of the object on the surface. Okay, so if, for example, your mate is standing on you, right? You are the surface that your mate is standing on, right? So in terms of your mate, he's experiencing a normal force going up, right? So that's you acting on your mate because you are now the surface, right? But then there must be a equal and opposite force that is acting on you. And that force going down is the force of your mate on you. Okay, so these are our action-reaction pairs in terms of Newton's third law. Okay, so let's look at some examples. So let's say we've got this cube, and this cube is just chilling there, not doing anything. So in that case, the forces acting on it is Fg going up, Fg going down, and the normal force going up. And in this instance here, because the cube's not going anywhere, by Newton's first law, Fg is equal to the normal force. Okay, but let's say, for example, we've got this cube here. Now, this cube has got an upwards applied force acting on it, which means that there's an x component, right? And there's going to be a y component, right? Now, again, this cube isn't moving, which means by Newton's first law, the net force acting on the cube is 0. So that means that the normal force going up and Fg going down can't be equal because all the forces going up have to be equal to all the forces going down. So in this instance, the normal force plus the y component going up must be equal to Fg going down. So in this instance here, you actually have a normal force that is less than Fg, right? Showing that normal isn't always just equal to Fg. Okay, in this instance here, you've got an applied force with an x component going that way, and now you've got a y component going down. So again, Newton's first law, forces are balanced because the object's not moving, or even if it was moving at constant velocity, the forces would still be balanced. But now here, you've got Fg going down and Fy going down. So in order for the object to remain at rest, the normal force going up has to be equal to the sum of these two things. So here, the normal force is equal to Fg going down plus Fy going down. So this is an instance where the normal force is actually greater than the force of gravitation, right? So not just equal to gravitation, it can be less than or it can be more than. Now, what's super important here is that you're able to link this to friction, right? So you know that the force of friction is equal to mu k, the coefficient of kinetic friction, multiplied by the normal force, right? So if you change the normal force, right, by increasing it or decreasing it, by having a y component from your applied force, right, because mu k is constant, you will then have a different frictional force, right? So in this instance here, you'd have a smaller friction force because your normal force is smaller because of this y component. And in this one here, you would actually have a higher frictional force, and that's because the normal force is greater due to that y component going down there. Okay, let's continue. Right, so let's say, for example, we've got a normal force on a plane here, right? Now, again, we like to break things up into components that are perpendicular and parallel to the surface that it's on, right? So this Fg here, right, we know we would like to break up into a perpendicular component, right, and a horizontal parallel component, Fg parallel. Okay. That might be a little bit difficult to see. Let me just change the color. Okay. And then, yeah, there's probably a static friction force there that's keeping it from going up. But then the forces that are perpendicular to the surface have to be balanced. So in this instance here, our normal force is going to be equal to Fg perpendicular. So here, N is equal to Fg perpendicular, right? Then something might be in free fall, right? So if something is in free fall, the only object acting on it is gravity. And if it's not on a surface, then the surface can't exert a force on it. So the normal force isn't even always there. In this instance here, the normal force would be 0. And then we've got this super interesting situation where maybe somebody, let me draw a hand. Yeah, somebody is pushing this block against the wall, right? And the block's not moving. So what forces are there? There's an applied force going this way, right? There's got to be friction going up, otherwise it would slide down the wall. And there's got to be Fg going down because gravity is always there if you're on a planet, right? Okay, which means in order for this block not to be going straight through the wall, there's got to be a balancing force coming this way. And it's the normal force. It's perpendicular to the surface. So here, in this interesting scenario, the normal force is equal to the applied force and doesn't even have anything to do with Fg. Okay, so the normal force is more than just Fg's little buddy, right? The normal force is the force of the surface acting on the object, perpendicular to the object, and it comes in many shapes and forms. And it's always important to think about the normal force in terms of friction as well, because a higher normal force means more friction, a lower normal force means there's going to be less friction. Okay, so here's another exercise for you to try. This one you will only have 2 minutes to complete because it's quite quick. Please find out. We've got this guy, he's standing on the crate. I want to know what the magnitude of the normal force is that's acting on the crate. Okay, fantastic. So let's end the poll there. So here, the most common result that we've got is 588 newtons, right? And then again, I'm happy to see that there's representation for all the answers. Always feel bad if I put up an answer and nobody selects it. Okay, cool. So let's see what the reality is here. Okay, right. So we are talking about the crate, right? So the crate is the important thing, right? So if we think about the forces that are acting on the crate, there's a gravitational force going down, right? There's a force of this lad who's standing on the crate. So I'm going to say F of B on C, F of boy on crate, right? And then there must be a normal force going up. Otherwise, the crate would simply fall right through that surface. And because the crate is not moving, well, those forces are balanced, right? So here the FG is easy because the crate is 20, so 20 times 9.8, right? And then we see that the mass of the boy is 40 kilograms. So if you go look and draw a free body diagram for the boy, right? The boy must have a normal force going up and an FG going down, right? Now that normal force going up for the boy, that is the action-reaction pair, the Newton's third law pair of this force of the boy on the crate, because the normal force on the boy is the crate that is pushing back up on the boy, which means that that normal force must have the same magnitude as that one there, but this normal force is equal to the FG. So this FG here is then 40 times 9.8, okay? And then 40 times 9.8 gives us 392. Okay, so this one here is 392. And thus the total normal force is equal to the forces going down. So it's the 392 going down plus the 20 times 9.8 going down, the mass, the weight of the crate, which is 196. And so we get the 588 newtons as the normal force there acting on the crate. Okay, so most of you got that correct. Well done. Okay, so then what we're going to do, predictably, is we're going to continue. Okay, so now we get to talk about Newton's second law. Okay, so if the net force acts on an object, the object will accelerate in the direction of the net force. This acceleration is directly proportional to the net force and inversely proportional to the mass of the object. Okay, so in simple terms, if you push something, it speeds up. Or if it was already moving, it can slow down. And it's going to speed up or slow down in the direction that you're pushing it. Yeah? And in mathematical terms, it means that F net is equal to MA, right? So up until now, we've been dealing with F net equals 0. Now we've got F net is equal to MA. So if we put this on a graph, F net is directly proportional to acceleration, and that direct proportion would look like that. As F net increases, acceleration increases for a constant mass. And we know that mass is then inversely proportional to acceleration. So if you have the same force, as you increase the mass, the acceleration would decrease. Or if you decrease the mass for the same force, then acceleration will increase. Right. So the most important thing here is that the forces and the components of forces that are in the same line of action as the acceleration are going to represent F net. And then the ones you can kind of forget about, if you're just trying to calculate acceleration, for example, is the forces and components of forces perpendicular to F net must be balanced, okay? So there can be an F net in the line of action of the acceleration, but perpendicular to that acceleration, all the forces must be balanced, okay? So when do you use this? Well, when the object is speeding up or if it's slowing down, right? So first law, if it's stationary or moving at constant velocity, F net equals 0. Second law, if the object is speeding up or the object is slowing down, F net equals mass times acceleration. Okay, so let's have a look here at an example. So we've got an outrageously colorful horse and it's dragging a 10-kilogram crate with an applied force of 400 newtons. The rope forms a 15-degree angle to the horizontal and the coefficient of kinetic friction is 0.1. Okay, so we've got to go and find the acceleration of the crate. Okay, so let's do this. Right, so again, it helps to understand all the forces that are acting here, right? So there's got to be a normal force going up. It's on a surface. we've got here this applied force that is acting at the 15-degree angle, right? Which means we've got an X component going to the right, and we've got a Y component going up. We've got to have some Fg going down. And because they mentioned there the coefficient of kinetic friction, we know that friction is going to be of import here. All right. So basically, if we want to apply the principles, we can say that, well, firstly, actually, we're dealing with vectors. So nominating a positive and negative direction is going to be very useful to us. So I'm going to take rightwards as positive, leftwards as negative. And then if we use the principle that in the acceleration line of action, that's where our F net is. So acceleration's going that way. And then perpendicular to that acceleration, everything's balanced, right? So that means if we go and say that our F net equals MA, right, and we take rightwards as positive, it means this X component, right, minus the friction is equal to MA, because those are the only two forces or components of forces that's in that horizontal line of action. And then what we also know is that the normal force plus Fy going up must be equal to Fg going down. And that's because the forces that are perpendicular to the acceleration, those have to be balanced. Okay, right. So here we can then start thinking, well, what can we actually sub in? So this Fx here, right, if we, let me just draw it a little bit more nicely. So if this is our 400 Newton force, right, then Fx would be here. Here's our 15-degree angle, and here's Fy. Okay, so Fx is adjacent to that 15-degree angle. So Fx is going to be 400 times the cos 15. Okay, that minus the friction is going to be equal to the mass times acceleration. A, we're trying to find. We know the mass of the crate is 10, so 10A. Okay, so here we've got an issue. So friction, we know, depends on the normal force, right? And because we've got this upwards component of the applied force, we know that we're going to have to do a little bit of work to find the normal force, right? So the normal force here is going to be equal to N plus Fy. So here, Fy is opposite that 15-degree angle. So we sine. So Fy is going to be 400 times sine 15. And that's going to be equal to Fg. And Fg is just the weight of the crate, right? So that's Fg equals mg. Crate is 10 times 9.8. Okay, and that allows us to solve for the normal. So the normal is going to be this 10 times 9.8, which is 98, minus 400 times the sine of 15. Okay, and let me just double check this here. 10 times 9.8 equals minus 400 times sine of 15. Okay, so that gives me an issue because I get a normal force of negative 5.53, which is not possible, which means that when I set this example, I made a little bit of a mistake. So what I'm going to do is I'm just going to make the mass of the crate 20 kilograms, right? And we'll see what that then does. Okay, so then instead of this, we're going to have 20 here. Okay, so I'm allowed to fix things on the fly. It's my example. So 20 times 9.8 minus 400 times sine of 15 is going to give us 92.47. Okay, so then the normal force is 92.47. And then I just note here, I used the mass of the crate as well. So I'm going to change that there. Okay, so now we've got the normal force. We're doing this so we can find the frictional force. So we know that the force of friction is equal to mu k, right, multiplied by n. Now, we know what mu k is. That's going to be 0.1. And we know that n is the 92.47 that we just got. So 92.47, and then we go 0.1 times the 92.47, and that, unsurprisingly, is 9.25. Okay, so that's then the frictional force, so we can sub that in for friction. 9.25, and then we're actually home and away, because we see in this particular equation here, the only thing that's missing is acceleration, and so we can go solve for acceleration. So 400 times the cos of 15 minus 9.25 gives us 377.12, and then we just need to divide that by 20, and then we get 18.86. So the acceleration here is going to be 18.86 meters per squared second, and that's going to be towards the right because that's the direction in which the net force goes. Cool. Okay. So that's our example there. So the most important thing that it comes down to is that the forces in the line of action of the acceleration, that's F net, right? And then the forces that are perpendicular to that acceleration, those forces have to be balanced. Cool. Let's see another example here, right? So for this example, we have an outrageously blue man, and he's pushing a crate up a 25-degree incline. The mass of the crate is 5 kilograms, and the coefficient of friction is 0.2. Find the force with which the man is pushing if the crate accelerates at 0.5 meters per squared second up the slope. Okay. So in this instance, they've given us the acceleration. We've got to find out how hard this guy's pushing. Okay, so again, it really helps to understand what's going on in terms of forces. So we must have an applied force there going up. Let me just do this here. Sorry, I started writing using the Zoom functionality rather than the PowerPoint functionality. Spoiled for choice. Okay, so we've got an applied force going up, right? We've got a normal force going this way. That's going to be useful to us, right? There must be friction going down, right? And then we've got Fg going down like this, right? But Fg, as we know, isn't super useful when it's not perpendicular or parallel to the surface. So we want to take Fg and break it up into components, right? So we want to actually go find Fg perpendicular, right? And we want to find Fg parallel. And we know that this angle here, the angle between Fg and Fg perpendicular, is the same as the angle of the incline. So that's the 25-degree angle. Okay, cool. So what do we know? We know that the forces in the same line of action as the acceleration, that's F net, right? And the forces perpendicular to the acceleration, well, those have to be balanced. So that means that the normal force perpendicular to the slope has to be equal to Fg perpendicular. That's also perpendicular to the slope, but going down, right? Because that's perpendicular to the acceleration here. And we know, so again, positive direction is going to be going up, negative direction going down here. We know that for our F net equals ma, we only want to consider the forces or components of forces that's in that same direction as the acceleration. So here it's going to be the applied force minus the frictional force, which is then equal to our ma. Okay. Right, so again here we're given coefficient of kinetic friction, which means we've got to use the normal force in order to go find that frictional force. So here the normal is equal to Fg perpendicular going down. Now that perpendicular is next to the 25-degree angle, so we've got to use cos for Fg perpendicular, right? So this crate is 5 kilograms, so the mass, the weight would have been 5 times 9.8. So that's Fg, and we've got to multiply that then by cos of 25, because the perpendicular component is next to the 25-degree angle. So 5 times 9.8 times cos of 25 gives us an answer, and that answer is 44.41 newtons. Okay, so this has been the normal force, and then again to find friction, we know friction is equal to mu k times the normal force, which in this case is then going to be, excuse me, just having a technical moment. Okay, so in this instance, it's going to be the 0.2 multiplied by the normal force, which was the 44.41. 44.41, and let's see what that gives us. Okay, so times 0.2 is then equal to 8.88. Okay, and that's then our frictional force. So here the applied force minus that frictional force of 8.88 is equal to ma. The mass we know is going to be the same 5 kilograms it was earlier, and then the acceleration we know is 0.5. So note here, the acceleration we know is in the positive direction. So we are taking that into account. We are making that positive, and that then means that this Fa is going to be the 5 times 0.5 plus the 8.88, and then we get 11.38 newtons. Okay, so that then has to be the applied force with which this outrageously blue man is pushing this thing up the slope. Right, so then it's your turn once more. I'm going to give you an entire 4 minutes to do this. We've got a tractor that pulls a crate up a 30-degree slope, right? I want to find out what the magnitude of the acceleration is with which the crate is accelerating up the hill. Have a go at that. Okay, for the sake of time, we're just going to quickly go through this one so that we can get to what you all want to see, which is the two-body problems, right? So the results here is a 50-50 vote for 1.47 and 2.68. Let's see what the reality is. Okay, so here you've got the tractor. It's going up a slope, 30-degree incline, right? So we've got FA going that way. We've got friction coming this way. You'll have the normal force going up, right? And then here, I'm just going to skip to it, and I'm going to say FG perpendicular is going to come down here, and FG parallel is going to go in that direction there, right? So now for this instance here, we're going to have the F net equals MA, right? And that's now in the horizontal line of action, right? So here, the applied force, okay, again, need a positive direction and a negative direction. The applied force minus the frictional force minus FG parallel is going to be equal to MA, right? And then the normal force is equal to FG perpendicular. Okay, so again, if you draw your FG, right, then your FG perp is going to be something like this. Then your FG parallel is going to be here. This will be your 90-degree angle, and this will be the angle of the incline, the 30 degrees. Okay, so the crate has a mass of 30 kilograms. So that's going to be 30 times, and then FG perpendicular is next to the 30-degree angle. So that's 30 times cos 30 then. Oh, not 30, 30 times 9.8, because it's got to be weight, right? So 30 times 9.8 times cos of 30, right? And that's going to be 254.61 newtons, okay? And that then means that the frictional force is going to be the mu k 0.3 times this 251.61, 254 times 61. So that times 0.3 gives us an answer of 76.38. Okay, and then we know our FA was 300 newtons, right? That's minus the 76.38 minus FG parallel. So FG parallel is now opposite the 30-degree angle, so we use sine. So that's going to be 30 times 9.8 times sine 30. And that's going to be equal to MA, which is then 30A. And then so we can defer to our calculators. 300 minus 76.38 minus 30 times 9.8 times sine 30, right? Gives us an answer of 76.62 on the left-hand side. And then we divide that by 30, and that gives us an answer of acceleration is equal to 2.55 meters per squared second up the slope. Okay, so if you didn't get the time to quite get to that, that's okay, as long as you were on the right track. Okay, so very quickly, Newton's third law. When object A exerts a force on object B simultaneously exerts a force of equal magnitude on object A, but in the opposite direction, okay? So in simple terms, if you push on something, it's going to push back. An important principle is that the two forces are acting on different objects, and thus they can never balance each other out, okay? Because they're acting on different objects. So let's say, for example, we've got this miner that's pushing around a cart. So let's look at the force on the cart and the Newton's third law pair that corresponds to that force on the cart. Okay, so the cart's on Earth, it's got mass, there'll be a gravitational force of the Earth on the cart. That means that the Newton's third law pair is the gravitational force of the cart on the Earth. Okay, now the reason the cart falls to the Earth and not the Earth up to the cart is because the Earth has a huge mass, whereas the mass of the cart relatively is tiny, right? So that same force can accelerate the cart easily, but not the Earth upwards towards the cart, right? But that's the action-reaction pair. Earth on cart, reaction's got to be cart on Earth. Right? Then we've got a normal force that's on the surface, that's the surface acting on the cart. So that means the force of the cart on the surface is going to be the action-reaction pair. Then there's the frictional force of the surface on the cart, and that means there's a frictional force of the cart on the surface. So that friction one is weird, but basically the two objects that are exerting friction on each other have that same frictional force, just one on the other. So it's like rubbing your hands together. Both your hands get hot. It's not like just one hand gets hot and the other one doesn't. So friction acts on the one surface. It also acts on the other surface, but equal and opposite in direction. And then there's an applied force of the miner on the cart, which means there's a force of the cart on the miner. Okay, so that's just to illustrate Newton's third law. Most important thing is they act on different objects. Okay, so now two-body problems. So I've apparently got 2 minutes left, which means what I'm going to do is I'm going to take a little bit of the Q&A time just to be able to get through some principles here and then to do an example. Okay, so for two-body problems, the tips is be consistent in applying direction, okay? So the direction, positive and negative direction, is going to be crucial when it comes to being able to write F net equals MA equations that you can actually solve and get the correct answer. Understand the free body diagram for each of the objects. So in order to be able to write the F net equals MA equation, you first have to understand what forces are acting on the body. And so the free body diagram is going to be crucial for that. The magnitude of the connecting force is equal but opposite in direction. Now, the connecting force, what I mean by that is either tension, right, or whatever it is that connects the two objects. Sometimes it's just the two objects pushing on each other. Right, so let's look closely at direction. So the direction chosen as positive or negative has to be consistent for the system, right? So if this basket of puppies goes down, and that's the positive direction, what that means is that this crate would be moving to the right. And so the rightwards direction would be positive for the crate, and the leftwards direction would be negative for the crate. So that there's consistency. If the system moves in one way, it's all positive. If it moves in the other way, it's all negative. Right? Another one is this here. If, for example, this green kettlebell moves down and you take down as the positive direction, when green goes down, blue must go up. So as weird as this is, in order to have consistency in direction, the positive direction for the blue kettlebell will be upwards and the negative direction will be downwards. Okay, so it's all about being consistent. If the system moves in this way, it's got to be positive for everything. If it moves in the other way, whichever way these things move have to then be negative for everything else. Okay, then the magnitude of the connecting force is equal, but in opposite directions. So this opposite directions isn't always true if we've got pulleys, right? But basically here, this tension force here will be equal in magnitude to this tension force over here. The one will be in the negative direction and the other one will be in the positive direction, depending on what you chose as your positive and negative directions, right? But again, as I said, this connecting force doesn't necessarily have to be the tension in a rope. So here, if you have object A and object B, the connecting force is actually here. B is experiencing an F of A on B, and A is experiencing an F of B on A. And these two forces will be equal in magnitude and opposite in direction. Okay, so here's an example. A man pushes two crates, a 20-kilogram crate and a 25-kilogram crate, both of them with a force of 100 newtons. The frictional force on A is 40 newtons and the frictional force on B is 50 newtons. Find the force that object A exerts on object B. Okay, so as I said, first things first, we really want to make sure that we're certain about the direction. So here I'm going to take rightwards as the positive direction, leftwards as negative. And fortunately, because these two things are moving in the same line of action, it's easy to be consistent with that. Okay, then we've got to understand the forces. So B is experiencing a force that way, and that's the force of A on B, right? There'll be a normal force, there'll be a gravitational force, and there'll be a frictional force. So that's for object B. Then for object A is experiencing this applied force that this outrageously blue man is exerting on it. And then there'll be a frictional force opposing the motion of A. There'll be a normal going up. There'll be gravity going down, but there will also be this force of B on A, right? So that's basically B pushing back on A because A is pushing on B, right? Now here, our acceleration is going to be in the horizontal line of action, right? So we don't have to worry about the vertical forces, those cancel out, right? So if we go and look at object A and we want to do F net equals MA for A, right? We are going to have the FA in the positive direction minus the friction force minus the force of B on A, which is equal to the MA. And then if we do the same thing for B, okay, I realize it's confusing that I'm now doing A on the right and B on the left. This is my presentation. I'll do it as I please. Okay, so then for B in the positive direction, you've got F of A on B, right? Minus the force of friction, and that's going to be equal to MA. Okay, so here we're in a situation where we can solve simultaneously, right? And when you're in that situation, right, you've got to make sure that the two magnitudes of the variables that you have are the same. So here, what's the same for both things is acceleration, and this FA on B and FB on A is going to have exactly the same value as well as that acceleration there. So we've got to be able to sub in for everything else, right? So here we know the FA on B minus FF. Now, FF, we said frictional force on A is 40 newtons. So this is minus 40, and that's going to be equal to 20A. right? And then here, for object A, the applied force, right, from the man is 100. The frictional force is going to be 50, and there's some F of B on A, right? That's also acting on it, but we don't know what it is just yet. And then there's a mass of, oh, I've made a mistake here. Let me just fix this. So this was object B. So the mass here should be 25. Okay, thanks for bringing that to my attention. No one, I did it myself. Okay, so here the mass is 20, and then here multiplied by A. Okay, so we've got to make something the subject of the formula. I'm going to make FA on B the subject of the formula here. So it's 25A plus 40. And that means wherever I see this FA on B or FB on A, I can sub in 25A plus 40. So 100 minus 50 minus 25A plus 40 is going to be equal to 20A, right? 100 minus 50 is 50. Okay, and that's then minus 25A minus 40 is equal to 20A. Okay, so when minus 25A goes to the other side, it becomes plus 25A. So that's going to be 45A. And then 50 minus 40 is 10, right? And then 10 divided by 45 is 0.22. Okay, so acceleration is going to be 0.22 meters per squared second towards the right. Okay, and then if you desire to go find the FA on B, you can simply go substitute that in there. So 25 times 0.22 plus 40, and that would then be 25 times answer plus 40. So then that force that the two things are exerting on each other was 45.56 newtons. Okay, so that then, in somewhat timeous fashion, concludes what I wanted to share with you as far as presentation is concerned. At this point, we can then move on to the Q&A section of our presentation. Right, so let's see here under Q&A, there are no open questions currently. So what we can do is those of you who are still here, you can raise your hand if you would like to ask a question. And once you have raised your hand, I will then be able to give you the opportunity to speak in order to ask your question. So please, if you do have a question, please use the Zoom functionality and raise your hand. Okay, and if you are tempted to leave just now, just because you don't have a question, we do have some exciting news to share with you at the end of the webinar about a promotion that we are running. So if you don't have a question, please stick around just to get that information. Okay, any questions? Just use the Zoom functionality in order to raise your hand. I take the fact that there are no questions to mean that I did such a wonderful presentation that you understand everything perfectly and have absolutely nothing to ask. Okay, in that case there, what I'm going to do is I am going to end, oh wait, there's something in Q&A. It says, sir, please explain the static kinetic frictional force. Absolutely. Let's talk about the static kinetic frictional force. Okay, so let's say, for example, there's something very heavy and you'd like to push on that something heavy. So let's say there's this really big box, right? And this box is 100 kilograms, super heavy. And then there's you, and you decide, okay, I'm going to go push on this box, right? And I want to move the box. Now, in reality, most of us wouldn't be able to push hard enough to move the box. But let's say, for example, you push with 20 newtons of force. Okay, right? Now that 20 newtons of force isn't enough to actually go and move the box. So what does the free body diagram look like? So there's got to be a normal force going up. There's got to be gravitation going down. And because you're pushing on the box, there has to be 20 newtons of applied force going towards the right. Now, in this instance, if you've got the 20 newtons applied force going to the right and nothing else going to the left, then it would seem, what? There's a net force, and then the box has to accelerate. But we know in reality, if we push against a really, really heavy box with a light force, then it's not going to go anywhere. So there's got to be a force that's going this way, right? And that force that's going that way while the box is not moving is what we call static friction, right? So static is a word that means not moving, right? So as we apply that 20 Newton force, the static friction resists that 20 Newton force and is going to be 20 Newtons in the opposite direction. Now, what's interesting is the harder we push, the harder the greater the static friction becomes. So let's say our friend here comes and pushes with a 40 Newton force, right? And the box still doesn't move. Well, then the static friction is actually 60 Newtons, all right? And let's say that another friend comes and pushes with another 40 Newtons force, and that is just enough to get the box to start moving. Right? That just enough to get the box to start moving. That is what we call Fs max. It is the maximum static friction where if we push a little bit harder than that, we can overcome the friction and get this object to start moving. And this Fs max is equal to mu s. So now it's the coefficient of static friction rather than the coefficient of kinetic friction multiplied by n. Right? So basically it means that the magnitude of the static friction depends on the two surfaces, because that's what this coefficient depends on, and the normal force that's acting on the object, which usually relates to the weight of the object, but not always, because we looked at that quite closely, right? So basically static friction, it resists the applied force going to the right until you get to that point where you overcome the maximum static friction, and only then does the object move. Okay, I hope that answers that question, right? We've got another question here. It says, sir, please explain again why we could use sine for fx and cos for fy sometimes. Okay, now what's very important here is that you realize I'm not that old. And hopefully if you manage to join us for a meeting in future or with some tutoring, you'll not call me sir and you'll call me Heinrich so that I can actually feel my age. Okay, so the question was, why can we sometimes use cos x? Why can we sometimes use sine x? Okay, so let's say, for example, we've got this force here, and this force is 50 Newtons, right? And we're told that this force acts at a 30-degree angle to the horizontal. Okay. So there are two triangles that you can always draw when you're trying to create the components of forces. So the one triangle would possibly look something like this, where we first draw the x component and then draw the y component. Okay, so that's a perfectly valid force triangle, right? But it's also possible to draw a force triangle where we first draw the y component and then the x component, right? So we can start by going up with the y component and then to the right with the x component like that. And this 50 Newtons is the resultant of the two red forces as well as the resultant of the two yellow forces, right? So these two sets of components are still the same. That Fy and that Fy is still the same. You can see their direction is the same, their magnitude is the same. Same for the Fx and the Fx. But here, this is a 90-degree angle, right? Which means that this must then be a 60-degree angle, so that 60 plus 30 is going to be equal to 90, right? So if you choose to draw your force diagram in this yellow way, right, then to find Fx, you've got to use sine because it's opposite the 60-degree angle. So there, Fx would be 50 times sine of 60, okay? And then Fy would be next to the 60-degree angle. So Fy would then be equal to 50 times cos of 60. Okay, but then if we go and do it the red way, right, then Fy is opposite the 30-degree angle. So in the red one, Fy is equal to 50 times, opposite means sine of 30, or Fx must then be equal to something to do with cos, because it's adjacent. So 50 times cos 30. Okay, so how on earth can these two things be the same? We're then claiming that 50 times sine 60 is exactly the same thing as 50 times cos 30, which means that we're actually claiming that sine 60 is equal to cos 30, right? And if you go and use your calculator, you actually find that sine 60 is root 3 over 2, and cos 30 is also root 3 over 2. And so these two things give you exactly the same answer. So basically, because we can draw our force triangle in two different ways, right, we can either use the one angle or the other angle. So what's important is that we understand what our force triangle looks like, and we can either draw the yellow one, which is perfectly fine, or we can draw the red one, which is perfectly fine. And most people build up a preference of how they prefer to draw their force triangle, right? But then in terms of the triangle that you've drawn, you've got to include the angle and then use that angle to decide about opposite and adjacent. Because if you're given an example, like for example, tension there of something that's hanging from a ceiling, and they tell you that this is 30 degrees, right? If you go use that 30 degrees and say that, for example, I always use sine for the y component, then you're going to get it wrong, because here the y component is actually next to the 30 degrees and not opposite the 30 degrees, right? So I hope that answers your question. Okay. So then we've got Mr. Hendrick. Please explain Newton's second law and its applications. Okay, so I think the short answer that I can give you for that is that the most important thing with Newton's second law is that when you've got your acceleration, the net force, right, is going to be in the line of action of that acceleration. So the net force is going to be all the forces in that same line of action, plus the components of forces in that same line of action. And then perpendicular to that acceleration, all the forces or components of forces will be balanced. So if you can break forces into components and then write an equation, F net equals ma for one, and basically F net equals 0 for the other one, then you should be able to solve that algebraically. Okay, then we've got a question here. Please explain the term inertia, right? So inertia is closely linked to Newton's first law, right? Where Newton's first law says, when we don't do something to something, it keeps doing what it's doing. Or in plainer terms, things keep doing what they're doing unless we do something to it, right? So inertia is a resistance to that keeping to do what it's doing. So if something has a higher inertia, then we require more force in order to get it to do something else. And inertia is something that increases with mass. So for example, if a truck is rolling down the street, it's a lot more difficult to get that truck to stop doing what it's doing than it is to stop a shopping cart to roll down the street or something like that. So inertia is a property of a body that causes it to resist a change in its motion. And the more mass the body has, the more it's going to resist that change in motion. Okay. And then what we've got left here is just explaining the law of universal gravitation. Okay, so a very quick one about the law of universal gravitation is that it's pretty much the same as Coulomb's law as far as calculations go. So if you can do calculations using Coulomb's law, then you can use Newton's law of universal gravitation. So it says that the force of gravitation between two objects is going to be g, which is a constant, times m1 times m2 over r squared, right? Where m is the mass of the first object, m the mass of the second object, and r is the distance between the center of the objects in meters, right? So it's often going to be given in kilometers, but we need to convert it into meters. And here, these masses are going to be in kilograms, right? Now, a super important thing to know about Newton's universal law of gravitation is that it's only attraction, right? So there are no repulsive forces of gravity. Gravitation is always an attractive force. And it says that every object in the universe attracts every other object in the universe. But gravitation, in the bigger schemes of things, is actually a really weak force. So because these two objects in my hand have a very small mass, the force of attraction between them can hardly be measured in terms of gravity. We need really, really large masses in order for gravity to start being apparent. And that's why gravity on Earth, we basically just notice the Earth's gravitational pull on the things around it. And that's due to the massive mass of the Earth. Right. So to link this to some of the other Newton's laws, right? If you say, for example, have the Earth and you have the moon, okay? The gravitation that the Earth exerts on the moon. So that Fg that the Earth exerts on the moon exerts exactly the same Fg on Earth, right? So those two are then Newton's third law pairs, right? Same in magnitude, opposite in direction, right? So when you calculate this Fg, it's the Fg that's acting on both objects. Then if you combine Newton's second law, with this here, you can actually show that gravitational acceleration is independent of the mass that's being accelerated. Okay, so here we've got this Fg equals g m1 m2 over r squared, right? So let's say, for example, that the only force that's acting is gravity, right? So, okay, let's start with F net equals ma. So that's now Newton's second law, F net equals ma. After that, if the only force acting is gravity, i.e. the object is in free fall, then F net becomes Fg, right? But then the acceleration that we get from that, we don't call A anymore, we tend to call it G, right? So this Fg equals mg is just F net equals ma when the only force that acts is gravity. Now here you might note that this Fg here and this Fg here are the same, which means we can equate these two equations. So that means mg, where this mass is the mass of the object that's on Earth or on the planet, so I'm going to call it m2, that mg is then equal to g m1 m2 over r squared. And because m2 then is on both sides of the equation, if you divide both sides by m2, the m2s are going to cancel out. And you get here that g is equal to g m1 over r squared. So the gravitational acceleration that a body experiences depends only on the mass of the thing that's accelerating it. So if you drop something, it'll be the mass of Earth and the distance between that object and the center of the planet. And that's why if in a vacuum you drop a cannonball and you drop a feather, both of those things are going to accelerate down towards the Earth at 9.8 meters per squared second. Okay, so thank you for that question, right? So that then I think is as much questions as have been asked. So since we don't have any hands raised, I think we can now go to that part where we let you know what you can do in order to get in touch with us. So the first thing we'd like to offer you is if you join Learning Space Tuition in September, we will waive your registration fee and we will give you 20% off your first month's fees. Secondly, if you want to get to know us, but you're not sure, you can book a group lesson with Learning Space Tuition in the month of September for only 99 Rand. So get in contact with us, tell us that you watched our webinar, and we will give you a group lesson for only 99 Rand so you can get to know us and we can get to know you. And then the last thing before you sign off, please finish our or complete our outro poll so that we can see just how you guys found the webinar. And then lastly, remember this is a series of webinars. So if you found this to be useful, there still is a stoichiometry and a functions webinar that you can attend, but also if it helped you, it might help your friends. So please let your friends know about the webinars that we are doing. And then lastly, thank you so much for joining. Thank you so much for taking this time on a Wednesday to go spend this time with me. I really enjoyed presenting this webinar, and I'm really happy that those of you that turned out did turn out. Thank you very much and have a fantastic evening.